Hello, and welcome to a little video about Target 4C, where we're going to be exploring the transformations of exponential functions. Number one is the graph called a of x equals 2 to the power of x. This is going to be our parent function. A parent function is our original non-transformed function. We don't call the transformed functions children's functions, we still just call them transformed functions, but we do call the original graph the parent. So, let's graph this original parent function. All right. The way I'm going to do this is in my calculator. I will plug in the x's into the x to find what y is. All right. When I plug in -2, I get, whoa, let me fix that real quick. I get 1/4. When I plug in -1, I get 1/2. When I plug in 0, we get 1. When I plug in 1, I get 2. And when I plug in 2, we get 4. The table gives us coordinates, right? So don't forget, this is actually -2, 1/4, etc., right? Your x and your y. Now, our parent function, this exponential function, also has an asymptote. The asymptote is a line that cannot be crossed. The reason that it cannot be crossed is because there is nothing we can plug into our function to get whatever y that is. In this case, in our parent function, there is nothing, no number that you could possibly think of that you could plug into x to get 0 as an answer. Our fractions, so the more negative we go with our x's, the fractions will get smaller and smaller, but we will never ever reach 0. So the way we graph an asymptote is with a dashed line, because technically it's invisible. If you ever graphed this function on a graphing calculator or say on Desmos, you'll just see the flattening out of our function like we saw when we just started graphing them in Target 4B. But we draw it when we were learning about them. We'll draw the asymptote so we can see what line we cannot cross. Okay, let's graph the points. -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. And there's that flattening out. Whoops, that does not look good. Let's try that again. There's the flattening out of the function that happens. There we go. Now let's see how every graph we do after here compares to this parent function, this original function. All right. So for number 2, we have b of x equals 2 to the power of x plus 3. All right. Let's plug in the x's and see how it compares with the parent. When I plug in -2, I get 3.25. When I plug in -1, I get 3.5. When I plug in 0, I get 4. Plug in 1, I get 5. And when I plug in 2, I get 7. Now I'll draw the asymptote here in a second. But first, let's graph the points, and then we can discuss the asymptote. All right, -2, 3.25. -1, 3.5. 0, 4, 1, 5, 2, 7. Now compared to the original graph, which direction did our points move? Hopefully you can see that they moved upwards. Now, on our graph, what goes up and down, the x's or the y's? It's the y's. So if we went up 3 spots, because we went up 3 plus 3, then our y, our asymptote y equals 0, also changes, and it goes up 3 to y equals 3. And here you can kind of see that flattening will happen higher up right there. Beautiful. So adding 3 on the outside of our function moved it up 3 spots. So let's go to number 6 where we're going to write this down. Oh, actually, I already wrote it down. I guess to save some time on this video. Number 6 asks us the similarities between a of x and b of x. Well, the similarities is that they look the same, but adding 3 to 2 of x moved it up 3. All right, let's do the next one and see what happens. All right, plugging this into my calculator. When I plug in -2, I get -275. When I plug in -1, I get -2.5. When I plug in 0, I get -2. When I plug in 1, I get -1, and when I plug in 2, I get +1. Let's graph that. I'm actually going to just expand my graph a little bit. -2, -275, -1, -2.5, 0, 2, 1, -1, 2, 1. Well, compared to our parent graph, it looks like our dots all moved down. So, just like before, our asymptote also moved down. So our asymptote is going to be at -3 this time. All right, let's draw it. And then we answer the number 7. A and C look the same, but subtracting 3 moved it down 3. We got 2 more to try, and these are a little different. Well, of course, we only have 2 directions left, but you should notice that the adding and subtracting of 3 that's happening in number 4 and number 5 is in the exponent. So that makes it special. Let's see which direction adding 3 takes our graph. Now remember, we went up and down, so all we have left now is right and left. So in your head, think, does +3 move us to the right or to the left? You made your guess? Awesome. Now, before I plug anything in, left and right is our x's, so our asymptote is not going to change because we're not moving up and down. So y equals 0 is our asymptote. I'm just going to write that down and get started plugging things in. When I plug in -2, I get 2. When I plug in -1, I get 4. When I plug in 0, I get 8. 16 when I plug in 1, and 32 when I plug in 2. Let's graph it. Here's y equals 0, -2, 2, -1, 4, 0, 8, and I can't graph the rest, and I'm just gonna draw it here. So, compared to the parent graph, the original, which direction did we move? So here's the original one, and here's number 4. If you guessed that adding 3 will move us to the left, you were right. These graphs look the same, but adding 3 to the exponent moved it left 3. We only have one direction left to talk about, but let's do it anyways to see how it looks. In number 5, we're subtracting 3 in the exponent, which is going to take us to the right. Moving to the right does not change the y's, it changes the x's, so our asymptote stays at y equals 0. Let's plug in these numbers. When I plug in -2, I'm going to get a crazy, tiny fraction, 1 over 32. Then I'm going to get 1/16, 1/8, 1/4, 1/2. You know what? I'm going to do one more. I'm going to plug in 3. Because I know if I plug in 3, I'm going to get 1. There we go. A nice whole number. I'm going to start with that. 3, 1. 2, 1/2. 1, 1/4. I'm going to guess the 1/8. I don't think I can draw those other fractions. That's too tiny. There we go. So our graph was moved to the right. And that's what I wrote for number 9. They look the same, but subtracting 3 from the exponent moved it to the right. Number 10, I ask us, for each graph, if any, did the asymptotes change? Well, the asymptotes changed for graphs B and C. For graphs B and C, the asymptote changed because we moved up and down, which changes the y's. Asymptote moves up and down too. Okay, so those are the transformations. Let's explore them a little further, but more algebraically than just graphically. When we think of a parent function, we think a base to the power of x. And the possible transformations that we are exploring this year, you will learn more as your math career moves on, is adding and subtracting to the exponent and outside of the function. These are going to be vertical and horizontal transformations. The vertical translations are going to be up and down. As we discovered yesterday, adding moves it up. Adding outside of the exponent moves units up, and subtracting moves it down. Oh, I don't like that. I'm going to highlight that again. Plus 5 up, plus and down. Then our horizontal transformations, which happen within the exponents and are really funky because subtracting goes right and adding moves us left. I know that is really counterintuitive. There is a pretty decent reason for it. You'll learn about it more deeply next year. But x's are always going to be opposites when we're looking at transformations. Always, always. That is not going to be different any other year you learn it. So let's practice just writing these functions after the translations described. So we're going to write a new equation, 4 to the 5th x, after each transformation. Okay, so number 1 asks us to translate it 2 units up. So h prime of x, that little prime means it's transformed. 4/5 x, if I want to move it up, I'm going to add 2 on the outside. Now let's translate it down. Similar idea. Whoops, I didn't change it to the pencil. H prime of x equals 4/5 to the power of x. And this time we're going to translate it left 7 units. Transforming something left 7 units is adding 7 to the exponent. It's very important that you make sure your exponents are floating, okay? That's why we practice that so much. Next, let's translate it to the right. So h prime of x would be 4/5 to the power of x. When we shift right, we are going to be subtracting from the exponent. And lastly, let's move it down 15, and that's where we're going to be subtracting outside of the function. Down 15. Awesome. Number 2, write the equation of the function after the translation described. f of x equals 5x. After a translation, 5 to the right, 4 to the right, and 3 down. And then let's write an equation for the asymptote. Okay, so f of x equals 5 to the power of x. If we're going to go to the right 4, we're going to subtract 4 up in the exponent. And if we're going to go down 3, we're going to subtract 3 outside of the function. Now we're asymptote. Our asymptote travels with movements up and down. We learned that in the previous section when we were graphing. So our asymptote is directly related to up and down. So if it started at y equals 0, we transformed it 3 units down. We get y equals -3 for our asymptote. Let's try that one more time with number 3. Here's g of x. Let's translate it 10 units to the left and 7 units up. And then we'll write the asymptote. Again, the asymptote is going to be directly related to our movements up and down. All right, so g prime of x equals 3 times 2 to the power of x plus 10 up in the exponent because that's a movement to the left, and then plus 7 on the outside because that's 7 up. 7 up. Our asymptote is going to be y equals 7 because it moves up with the function. Number 4 and number 5, we're going to be taking this function and we're going to be doing the transformations to it quite physically. So imagine as if we were able to pick up the function from the graph and move it. All right. It doesn't have an asymptote drawn in, so I'm going to do that. This asymptote Looks like it's at 0. That's where it's flattening out. So I'm just going to draw it. Okay. And I'm going to move this 7 down. All right. Let's move 7 down. I'm going to pick 2 nice points and move those down. And then don't forget, we got to move the asymptote down too. Let's do that first. I'm going to move the asymptote down 1, 2, 3, 4, 5, 6, 7. Here's our asymptote. All right, now let's create some points. I'll use the y-intercept and then this one. Let's move them down. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Whoops. Hopefully you draw it better. But here's our new graph, moved down 7. So after the translation down 7, our asymptote is at -7. Fantastic. In number 5, we're going to translate our function to the left. It looks like here our asymptote is at y equals 0 again. If we're going to move to the left, our asymptote won't change because our asymptotes are y equals is, and moving to the left is for the x's. So after translating, our asymptote stays the same. Let's translate. I'm going to use this point. No, I didn't want pink. I wanted purple. Let's fix that. Now I want an eraser. What are we doing here, pencil? Thank you. Okay. I'm going to use this point, and do I have any nice points here? Oh, here we go. All right. How many to the left are we going? 4. Okay. A 1, a 2, a 3, a 4. A 1, a 2, a 3, a 4. Here's our new function. Beautiful. Number 12. Let's translate this function 3 units up and 5 to the right. We'll graph it and we'll talk about the domain, range, and asymptote. And that's the last one. Okay, 3 up and 5 to the right. Okay. Remember, our asymptote goes up and down with our function. So our asymptote's going to be directly linked to that. Y equals 3. I'm going to draw that in. 1, 2, 3. Boop, 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 boop. Okay, let's move up 3. I'm going to use this point. Actually, I want to draw that not in pink. I'll do that in black, this point. And I want to do this point. Ooh, and then there's this point. I'm going to use 3 here. Is that overkill? Maybe. I'm going to change my mind. I want to do this one. You know, the more points, the more accurate. Oh, that's fine. All right. 3 up, 5 right. 1, 2, 3. And where's green? There it is. 1, 2, 3, 4, 5. Cool. 1, 2, 3. 1, 2, 3, 4, 5. Last one. 1, 2, 3. 1, 2, 3, 4, 5. There are my 3 new points. I'm going to connect them with purple. There's our new function. Okay, domain and range. Domain is our x's. Our x's go from right to left. In this case, I can have any x I want. I can plug in any positive number and any negative number, and that'll be okay. I know this because I have an arrow over here pointing to the right, and this one pointing to the left. Now I know it's pointing down, but if you imagine it, it's kind of going down to the left, to the left, to the left, to the left, to the left. It's just we don't have space. So if we're going all the way to the right and all the way to the left, we're doing all the positives and all the negatives. Our domain is all real numbers. For our range, we are going to be looking at our y's. Now it looks like we have an asymptote, but everything below that asymptote is okay with us. So the asymptote is at 3. That means our y's must be less than 3. Beautiful. If you have any questions, please let me know. I do have one more thing I want to say. That's why that felt like a weird ending. For domain, for all real numbers, we really should say negative infinity to positive infinity. Yeah, that is how we did it previously. I don't know why I wrote all real numbers. I knew that looked weird. I mean, it's the same thing. I don't need to erase it or cross it out. But from negative infinity to positive infinity, because that's all the way left and all the way right. And the range says just below 3, because that's where our graph exists. Okay, now we're done. If you have any questions, please let me know. Otherwise, have a wonderful rest of whatever day it is for you. Bye!